Okay. Okay, so last time we ended here. We have talked about the regularization. Yeah, actually, regularization is not the only thing we talked about last time. Actually, it's something more interesting about more efficient ways to update parameters in gradient descent. Okay, so it's actually momentum, RMS prop, and atom algorithm that we covered. Okay, so these, the purpose of these more advanced or fancier ways to update parameters is basically to make the training faster, make the training more efficient, so that the theoretical minimum point is reached within shorter time. Okay, you want to make the search more efficient, not going to random directions. Okay, so and the L2 one is actually belongs to a different purpose. L2 regularization is to basically deal with the overfitting. Okay, and actually, speaking of overfitting, we know that neural networks have actually contain a lot more parameters than simpler models. Okay, we have that many layers, and each layer we have tens or even hundreds of neurons or neuron units that are associated with parameters. So with that many number of units, it's very easy to have the model overfitted to our training data sets. Okay, and we definitely want to avoid that. So L2 regularization is a general form, a general way to alleviate that overfitting issue, and it's basically on the same principle used with the same principle with the L2 regularization that we have covered for logistic regression, right? It's a modification of the loss function with this so-called Frobenius norm, okay, which essentially measures the magnitude of all the parameters. We put this term into the cost function. So while we are minimizing the cost, we are also minimizing together. We are minimizing the magnitude. So that's the magnitude of the parameters got punished. It's not getting overly big, right? It's not getting too big. So that's why we use a term called weight decay. The term weight is refers to all the weight matrices. Okay, it refers to all the parameters in the weight matrices. So we let the weight decay so that it's not getting too big. Okay, so that's basically how the weight decay is from. And in PyTorch, it's quite easy to set weight decay, right? If really overfitting is an issue, then we can let the weight decay turn. We can turn on the weight decay, and so that the model does not fit too much to the training set. All right, and other than L2, what we're gonna focus on first today is another technique for the regularization, which is called dropout. And dropout is a more commonly used method that are particularly suitable for neural network models. Okay. All right, and as the name indicates, it's actually quite straightforward to understand what this technique means. So given such a deep neural network, if we don't use dropouts, then that means we keep everything as they are in the network. All neurons, all these arrows, all these weight parameters, they will be there for our usage. Okay, so if we applied some dropouts, then that means we delete or remove some units in the hidden layers. Okay, we can do that randomly in a random style, like we remove these 4 neurons. So that now the resulting model would be like this, right? Okay, I think I left one behind, okay? But anyway, you get the idea that we remove some of the neurons. So now the model, the structure of the network becomes more irregular, right? Because we randomly selected something and delete all these neurons. So it's a messier network we get. And actually this seemingly simple operation on the network has a huge difference on the training results. So before we look into the results, let's first look at how in practice this is gonna be affect our outputs. So actually for different input examples, we're gonna we're gonna drop out different new units, okay? So like for the input example 1, we're gonna drop out those red units, okay? But to drop out some unit doesn't mean that we delete them permanently. We still keep a backup, like we still have the information about where they ought to be if it's a complete network, right? We remember their original positions, their original connections to the previous layers and the next layer. So we keep those information. We just disable them, kind of disable them. Yeah, I have a question. So yeah, can you go ahead and speak? Sachin?
Yeah, Professor. Yeah, Professor. I have a question. Instead of removing this neurons, if we just put the weights as 0, some of the weights as 0, that is also called as dropout, or there's nothing like that, those things?
You mean by like make that particularly to make those parameters 0, right?
Yeah, like we have a weight matrix, a few elements, if you put at 0, that will affect as like not contributing to that.
Yes. So like if you let the inputs to be let one row in one in a weight matrix to be 0, then that'll have the same effect. Okay, so your question, I think it has something to do with the implementation details, right? So in the next few slides, I have one slide showing that in NumPy how we gonna implement dropout, and it's actually quite similar to the way that you mentioned. We also we can like multiply the outputs with some additional matrix that are masked with 0 or 1s, and only those units corresponding to the 1s are kept. And that is one way to implement dropouts. But I think in modern frameworks like PyTorch, TensorFlow, all these underlying implementations for the dropouts, they are highly optimized. And but the general principle is that we don't like permanently delete that unit. Like we can like create some masks that are either have 0 or 1s to mask out the outputs. So other than the inputs, so other than zero out all the inputs, we should also zero out the outputs. Okay, so it's not just the element, it is not just the weight matrix that need to be processed, but the outputs also needs to be handled. Yeah, but I think this is some useful discussion here. Anyway, so for a second example, we can have a different positions, or we can choose to drop out different units, and that is actually encouraged because we want different. We want to introduce more randomness during training. So the different mini batch or different data input examples should actually have different dropouts. Okay. And now we can, speaking of the implementation of the dropouts, we can actually use a mask that consist of 0 and 1s and we multiply that mask with the activations from all the layers. Okay, so we actually doesn't need to be like initialize or to make all the parameters, the corresponding rows for parameters to be 0. We just need to deal with the outputs, like, because we, from the perspective, I mean, from the effect, right? We want the dropout to be effective, and the effect is that it doesn't output it doesn't produce the output. So all we need to do is to deal with the output. Okay, so we can use a mask and multiply that mask with the activations from all the layers. Okay, and the mask, the way how we initialize the masks is basically very random style. So that the randomness is introduced, and we can also we should also like use a probability to control the proportion of units being dropped out. Okay, like in the example of this NumPy code, we can like define the probability to be 0.8, and that is the probability that some units, that 80% of the units are kept. Okay, so if we sample some random numbers from the uniform distribution with such a shape and use these logical comparison statements so that we can produce a mask, and this mask consists of Boolean values that actually correspond to the 0 or 1s. And then we use this mask and apply the point-wise multiplication with the original activation. Okay, and this actually, there is a divided by prob, and this step is quite interesting because after we have dropped some units, then in total, the total magnitude or the total values of the activation should actually drop because we remove some of the elements. Okay, but in order to make sure that the outputs, the grand total is almost at the same level, then we need to scale up the activations by a little bit, which is proportional, which is inversely proportional to the dropout, to the keep probability. Okay, so we call this inverted dropout, so that the grand total got basically increased a little bit. Okay, so that's the magnitude remains almost the same regardless of the dropout probability. Okay, so this will make the test time easier. Okay, all right, so in NumPy, like we can, so this is a demo showing that the activations is like this. It's a 4x3 matrix, right? 4x3 array that have random activation values. Then we can create a mask in this way, right? With the same shape as the activation matrix A. So if you look at the mask, it consists of true and false. And in Python or in NumPy, it's the true is considered as 1 and the false is treated as 0. So if we like multiply A and mask together, we can see that those elements that has false will be removed, will be actually eliminated, because it's like these elements times the false, and the false is treated as 0. And we can also see that because we have these inverted dropouts, some values, they are greater than the original values. Okay, these two values, for example, they are greater than these two. They are 0.9 something, but now they are 1.2 something. So that's the total magnitude remains at the same level. Okay, so the more you drop out, say if I use 0.2 here, which means I only keep 20% of the activations, then this divided by 0.2, which means like times 5, which is a very large increase. So this is a very dynamic change of the magnitudes. Yeah, so it's basically the total magnitude of the entire area. Yes, that's true. All right, and in the back, so the dropout is also like necessary in the back, because in the forward pass, some neurons are not uh, so I see Devon's question, like, why is it important to keep the, yeah, so the thing with dropouts is that we actually, in the training stage, we like dropped some units in the activations, and in the testing time. So when we are during the testing stage, when the model is done, then we don't drop out the units, right? So when when we test the model, we don't randomly select units and then drop it out, because every unit, every neuron in the model that is already trained contain useful piece of information. There's no reason that we want to remove some elements, remove some neurons when we are testing a model. Okay, so because in the testing model we include all the neurons, so it's important that in the training stage that we need to treat the total magnitude as if that's all the neurons are present, all the neurons exist. So after we have removed some neurons, we basically need to scale up the magnitude for the other remaining neurons, so that the model behaves as if that's the total magnitudes are like as if all the neurons are there. Okay, so that is for making the testing step more valid. Yeah, so I just mentioned that the max should be kept, because when we have conducted a forward pass, right, we need to immediately doing a backward. And when we do the backward, not all the neurons need to receive gradients, okay? Because some neurons, they are temporarily moved out. So we only need to use those that have that are kept, okay? So the mask should also be cached. It's like we need to use mask to filter out some units, some elements in the gradients, right? So it's basically the same idea as the forward pass. All right. And another details about the probabilities is like we can set different dropout rates, okay? So these dropouts rate can be different across layers, okay? So it's I think it's a very empirical setup. Like it depends on how the model looks like, and we can like have higher drop probabilities and lower probability for layer 1 and 2, and maybe we don't have dropout at the later layers. Yeah, that is very empirical choices. Okay, and let's see. Yeah, so for the test sign, for the test time, we don't use dropouts. We just use regular forward pass to make predictions. We don't apply dropouts because all the neurons are useful, contain some useful information. Okay. Okay. So in the original paper that the dropouts is developed, we can see that this figure actually plots the error rates in testing set. So it's basically, you can think of it as the performance on the test sets, and the x-axis is the so there are two types of curves. One curve, the above curve, is without dropouts, and with the dropouts, it has significantly smaller or lower error rate, which is a better performance on the test rate. Okay, and the training loss is higher if we apply dropouts. Okay, so that is also understandable because we fit the model less to the training data if we apply dropouts. Okay, because each time when we have a mini batch or when we have a new data example, we change the structure of the model. So in theory, the model should have worse performance on the training sets, right? Because we're making random changes. The model should not know the training data as good as those models without dropouts, okay? But that is okay. So it's a trade-off. We fit the training data worse, but the result is that we fit the testing data. We actually perform better on the testing data sets. Okay. All right. So because this is a technique that is so commonly used, and it's then the implementation in PyTorch is actually quite very easy to implement. So we just need a one sentence in the arguments. Like we can add a dropout line, okay? And this probability means that we drop out 20% of the neurons in that layer, okay? Okay. So regarding that question, how can we test better if we are training worse? We need to keep in mind that the training data sets and the test sets is they are essentially different. Say I have two cups. If I turn off the virtual background. So see, I have two cups. So if I train a model to recognize the type, the shape of a cup, and if I train my model on these steel cups made of steels and plastics, then and assuming that I used in my training data sets, I have a lot of these steels, cups made of steels, but in my testing sets, I have some pure plastics ones. So because the two data sets are so different, if my model fits too well to my training data sets, then it is very likely that it's not gonna recognize this plastic one, okay? So one thing what we can do is that to deliberately set some dropouts so that the model does not fit to this training data set too well. Okay, so the model is still able to generalize to the cups of other types. Okay, so maybe the model will focus more on the shapes rather than the materials. Okay, so that is an analogy because we deliberately remove some neurons during the training stage. So the model being trained in this way will not rely on too much fixed patterns in the data. It doesn't rely on too much, I would say, too much specificity in the training data set or idiosyncrasies in the training data, but it's recognized the more general patterns. Okay, so let's go to the next slide. I think there's some theoretical discussion about why dropouts works. Okay, I think it's a very interesting discussion here. So intuitively, we can say that because for each iteration we dropped out some units, then apparently we used smaller network. right? We drop some, like if we set the dropout probability to be 20%, then we use 20% less parameters. And we know that using less parameters is helpful to alleviate the overfitting, right? We are using less parameters. And also, we have a lot of randomness in the dropout process, like within between different data examples, we have different dropout masks generated, right? So each, like, it can be different mini batch from mini batch, okay? And that means all the neurons, all the units are randomly eliminated, okay? So that means we cannot, the training will not rely on certain features, okay? And the training stage, all the weights have to be spread out. All the weights have to be spread out, okay? So that's the generic, so the resulting model tend to make generic predictions, okay, instead of describing the idiosyncrasy in the training data sets or memorizing the specific patterns in the training data sets, okay? So the model is encouraged to capture the more general patterns. That is basically how we can explain why dropout works, okay? And actually, in practice, this effects or improvements from dropout is quite visible in practice. Like when we apply some dropout units, we can see that the testing accuracy immediately increases, okay? But as we show before in the slides, that there's a trade-off. So now, because to avoid overfitting is our concern now, so we don't expect that the model to have the best training performance if we want to achieve better testing performance. All right, so let's recap a little bit of the content so far. So dropout is to avoid overfitting. Then if there's no such overfitting issue, then we probably need not to use dropout. Okay, but it's almost always used in computer vision applications, okay? Because most of the computer vision tasks, like object detection, like background segmentation and so on, they usually lack training data sets, okay? And also the models have large number of parameters. It's very easy to overfit, okay? So it's quite often in CV tasks, okay? And actually there's an interesting talk here. It's given by Geoffrey Hinton. Actually, there's discussion over like how the dropout mechanism correlates to what's the real activities, like the neurons in our brains that have similar mechanism. Like some neurons will maybe stop connecting to the next one in a brain in an actual brain. So it's a pretty interesting talk to watch. All right, so that's for dropouts. So we together with L2 and the dropout, we have covered like the most common techniques for regularization and deep neural networks. And actually there's some other methods, and particularly we focus on this data augmentation. So one issue is that we have a very that one cost factor for overfitting is that we have a model that is very big, but we have too few data points. We have a too small data set to fit into the model, okay? But if we find that it's very hard or expensive to collect data or to manually label all the data sets, then the one option is that we can create some on top of the existing data points. Okay, it's called data augmentation. Okay, so it's a operation by making minor changes to existing data and treat them as if they were new data points. Like the traditional way is that we train, like we flip the images, we rotate, we crop, or we add some noise to that image. In this way, we can create we can make the training data set double or triple in size or even more. Okay, and nowadays, with the advance of generative adversarial network, or known as GANs, it's a type of technique that's use deep convolutional networks to generate very realistic images out of nothing, out of a random input. So this GANs model will be very useful in augment data sets. Okay, like if we have pictures, say I want to recognize this cup, okay, but I don't have a lot of images for cups, so I can like train a GAN model on top of the existing data sets, and then I will let the GANs model to generate images of the cups, okay, and then I will use the generated images as if they were the actual cups, okay, and I will build a classifier on top of these hybrid input data with actual cup images and the generated cup images. All right, that's the data augmentation as a way to regularize neural network models. Okay. So next, we will look at an issue that occurs during the training stage. How we it's actually a issue that is quite often when the model is deep. Okay, it's very commonly encountered issue, and we usually there's certain fixed ways to deal with the issue. It's called vanishing and exploding gradients. Okay, and the issue is like that for very deep models, the gradients can get extremely big or small. Okay, which will make the training difficult. So remember, when we first talk about gradient descent, we use a 1D function and we move around the theoretical minimal points, right? If we take a step that is too big, right? If the gradient is too big, then we will like miss the minimal points. So yeah, the thing is that if the gradients are too big, that is something we want to avoid. And also if the gradients vanishing, that is also not good, right? If the gradients are zeros, then we're basically learning nothing. No parameters will be updated with 0 as gradients. So we can deal with these vanishing or exploding gradients with basically several ways. Like first, we can initialize all the weight matrices, all the weights into proper values. Okay, so we'll look at this issue more closely. So how does this happen? Okay, so let's look at the forward pass, right? So let's assume that we use linear activation functions. Okay, so the activation function is a linear function. There's no sigmoid, no 10H or ReLU, okay? And all the biases are all 0. Then the activations at the last layer would be the chain of products of all the weight matrices before the last layer, right? From W1 to WL. Then let's think about the question. So if W is a like identical matrix, like there's only ones along these diagonal elements and all the other elements are zeros, then it probably works fine, right? Because 1 times 1 equals 1, right? If we apply matrix multiplication rules here. But what if W is a little bit larger, like we have 2's along the diagonals? Then in theory, we would have the last layer's outputs would be 2 to the power of L times X. Okay, what if the W is lower than 1? Then the activation would be 2 to the power of negative L, right? Because 0.5 is 2 to the power of negative 1. So if L is very large, say like 10, right? So 2 to the power of 10 is already 1024, right? 1024. So that is such a effect that we magnify, right? We are magnifying the inputs. We are the activations is growing too fast, right? If we don't, if the weight matrices, they have very large values, okay? And so is the process to the backward process. Like the gradients is also the exponential function of the number of layers. Okay, so that's why we would call it, sometimes if the weights is greater than 1, then the gradients is likely to explode, right? If the gradients is, if the weight matrices is between 0 and 1, if it's too small, then the gradients is likely to vanish. So both are extreme cases. So how do we handle this? Okay, one option is to initialize the weights properly. Okay, like if we look at the connection between one layer to the next, the Z's will be the inner product between the W, the weight matrix, the weight parameters, and the activations from the previous layers, right? So we want the W's to be small and has a variance that is close to 1 over n L minus 1. So this n L minus 1 is the number of neurons in the previous layer. Okay, because we cannot control the magnitudes of the previous activations. We can only control the magnitudes of the W's. W's are the parameters that we can initialize. Okay, so we can initialize W to such a within such a range, within such a variance range. Okay, so mathematically we can say that the variance of the Z's would be like the expectation of the W's times the variance plus expectation of A times the variance of W and the variance terms. Okay, so these are the mathematical basis for this conclusion, for this method. Okay, so it's okay to just remember the results here, the conclusion here. So a common practice is that we use such a way called Xavier initialization, which is to first generate some random numbers from a normal distribution, right? And scale it down to these square roots of this 1 over n, okay, depending on how many layers, how many neurons we have in the previous layer. And for ReLU, we can probably use a different coefficients like 2 here. So all these are from existing papers that after people have done a lot of different experiments. Okay, so the conclusion is that if we initialize the parameters in such a way, then it indeed helps reduce the vanishing and exploding gradients a lot. Okay, but actually it doesn't solve it all at once because the the process of training a neural network model is actually full of accidents. It's like, I don't know what happened, but my gradients just got vanished or just got exploded. These are all possible to occur. Okay, so we need to have something more dynamic we'll see later in the next slide. Okay, so in PyTorch, the Xavier normalization and the other normalization, other ways of normalization, they are actually already encapsulated. You can directly call these functions very conveniently. Okay, so if we want to deal with the dynamic exploding gradients issue that occurs a lot, quite often in training a model, we can simply use the way called clipping. Okay, this is a very simple way. It's just to limit the magnitude of gradients manually. Okay, we just set hard limits to tell the gradients that you should not suppress this hard limit. Okay, so in gradients, in PyTorch, we use such a gradient grad norm or gradient grad values, or we can write a custom function that we like set some threshold here, right? We're given the model, we set a threshold, then we will simply limit the values, okay? Limit the values, use this clamp to limit the magnitudes of those parameters between negative threshold and threshold. So these are actually very useful and easy to implement method when we want to decide, when we want to set a limit on the magnitudes of the parameters. All right. All right, so now let's speak of gradients. Sometimes when we train a model, it would be interesting, it would be helpful to check whether our implementations for the models are correct. Okay, so this is a technique called gradient checking. Okay, so we are curious about whether our computation for the dw, like the gradients for the w and the gradients for the b, are correct. What we can do is that okay, use an approximate way to compute the partial derivatives with respect to w and b, and then we compare the gradients. Okay, so these gradients are maybe computed through backpropagation. Okay, but we are not sure if backpropagation is correctly implemented. Then we can compare those approximated values with those gradients. Okay, and hoping that it do not differ too much. So what we can do with the approximation is that we like increase the values, input values for w's a little bit with this plus epsilon and minus epsilon, and we like measure how different the output will be, and use the difference in the outputs divided by the step of the change of the input, right? So this is a typical way of defining partial derivatives mathematically. Okay, so having these approximated values computed, we want to compare whether they are the same with dw and db. Okay, so in practice, actually, this is a technique that are useful if we want to implement something in NumPy. Okay, but I don't think people nowadays use it a lot because we have PyTorch, like frameworks like PyTorch that automatically handles the gradients for us. So I'm gonna drop this, skip this real quick. Okay. All right, then we finally reached the parts for the so-called batch norm. Okay, so actually, let's review a little bit. Okay, we from our last week's lecture, we start by these parts. All the optimization algorithms, their purpose is to make the training faster, right? And then we talk about regularization, right, with L2 and the dropouts. And then we talk about how to deal with the vanishing exploding gradients just a moment ago. So there's one term left, which is batch normalization. Okay, so the purpose of batch normalization is also to make the training faster. Okay, and actually, it's a technique that is so commonly used that we can see it nowadays almost everywhere. So in the now most recently, more very popular model GANs in the generated adversarial networks, the batch norm is like applied almost anywhere, everywhere within the GAN model. Okay. So I place it here in the first section, which is to make training faster, but actually it also had some effect to regularize the model, to help avoiding the overfitting issue. All right, so let's look at this batch norm operation. Okay, so it's first proposed in 2015 by Loaf and this, I don't know how to pronounce this name, Shagady maybe, yeah. So it's initially as a way to accelerate the training for deep neural networks. And the thought of this method is like that because typically when we train a model, we need to do some pre-processing on the inputs. What we usually do is that we move the, we will center the training data or the input data around 0, right? By subtracting the mean values. And also, we will like normalize it by dividing by the standard deviation or the variance of the data. So now the data would looks nicer in the distribution, right? It will be looks nicer in the feature space, and the resulting one of the result is that it makes training more efficient because the if we look at the gradient space or the parameter space, the contours of all the parameters will also be closer to a circle rather than an ellipse, right? So these two pictures contrast are something we have shown when we talk about why inputs need to be normalized. And I think it's near it's at the very beginning of this course, right? So the thought of batch norm is that we can apply the same technique not just to the input, but also to the output of hidden layers. Okay, because the output to the hidden layer, they are the input to the next layer, right? Because they are also the input. So why not we normalize the input? Okay, so X can be think of as A0. So all these A's, they all can be considered as input to some model. So theoretically, we should always normalize the inputs. Okay, so why not we also normalize the activations in all the layers? Okay, so in practice, we should do that, right? We should normalize to make the training for the parameters more efficient. Okay. All right. And in practice, what we usually do is to normalize the ZLs before the activation function, okay, rather than directly normalize the activations, okay. So it's called batch norm, and let's look at how batch norm is implemented. So for a layer, right, we will have Z's. So we are looking at a lot of input at the same time. It's a batched processing, right? We're not looking at one example, but a lot of examples with n examples in this mini batch. So it's capitalized L. So it's actually like this. It's like the first instance is the first column, right? It's from Z1 to Zn with 1 as the superscript, right? And second is Z1 to Zn with 2 as a superscript, okay? So that's all the Z's, okay? So what we can do is that, okay, given this matrix of Z, we will like compute the summation will compute the means for each row in this matrix. And each row actually corresponds to one feature, right? It's a summation of all the elements per row, right? And we will compute the mu's, okay? And each mu, we have mu1 to mu_n. Each mu corresponds to one feature. Okay, mu1 is correspond to the z1, mu2 to z2, and so on. All right, having the mu's available, we can have the sigmas also computed for each row. So the sigma is also a vector from sigma 1 to sigma n. Okay. Now we can compute the normalized z's, or we call z bar. Okay, so the z bar would be the results that the original z minus mu times divided by these square roots of sigma square. Okay, so it's like a with this epsilon to avoid the dividing by 0 issue. Okay, so it's basically in the sigma itself. Okay, so the z is actually something that we moved all the z's into a center, into a point that is centered around 0, and all the z's are also normalized. Okay, almost to the scale between 0 and 1. Not between 0 and 1, but it's it's almost a normal distribution with 0 as mean value and the 1 as standard deviations. Okay, so this is the so-called normalized outputs. Okay, we're not done yet. It's the first step of computing this z bar. Then we're gonna constructing something more complex, which is called the z tilde. Okay, so this z tilde is a combination like gamma times z bar plus beta. Okay, and this gamma and the beta are learnable parameters. Okay, so they are like additional parameters, and which means they should also be updated in the training iteration. Okay, they are not hyperparameters. They are not predetermined. They are part of the model. They are just like W and B's. Okay, but they are additional parameters. And this beta and gamma, they are also vectors. They correspond to each features. Okay. So the z tilde now, with the help of gamma and beta, it is more flexible. It can have different means and variance values other than 0 and 1. Okay, so now we can have z tilde. Okay, so the z tilde matrix is the final output after so much transformation, so much processing. We have original z to this z tilde, and each column is a z tilde, smaller z tilde in lowercase. Okay, and this z tilde, will be then feed into the activation functions. Okay, it is not the z directly, but the z tilde we will use. All right. If we put everything into a computation graph for neural networks, it'll be like this. Given the x as inputs, we will first apply w and b to compute the z's. These are usual operations. Okay, and then after z is computed, we will compute the z bars by computing the per row mean values, right? And z bar will be used to compute z tilde, right? Within these batch norm blocks, right? Batch norm blocks, we have z tilde computed from z from z bars, okay? And with additional gamma. So this gamma 1 and gamma beta 1, gamma 1 and the beta 1, they are associated with the first layer. They have the superscript that is same as the W and B's. All right, then we can have some A's, right? A is the function, activation functions applied to z tilde now. All right, the A's are applied to the next layer, and the next layer similarly will compute Z2, right? And Z bar 2, and Z tilde 2, and A2 as function of Z tilde 2. Okay, so now since the Z tilde, the way how we compute Z bars are like ZL minus mu. It's like a normalized, already normalized. So because the input Z bar here is normalized, then the original B here is no longer having an effect. Okay, because if you compute the average values for Z bar, they are actually 0. So the B will not be taking any effect. So the parameters left for each layer would be W, gamma, and beta. Okay, and the shapes of those parameters are like similar to the original network. All right. So now our network is modified by having this gamma and beta as new parameters. So, but the training stage is more or less the same. It's like with batch norm, we basically need to compute the gradients of W, dW, d gamma, and d beta, and update those parameters during the update stage. Okay, so we can do whatever techniques we have defined previously, like momentum, atom, upon these gradients for W, gamma, and beta, just like they are like their usual parameters. All right, so if we describe the computation graph for batch norm, it's actually a quite complex one because we have so many operations involved here. Like we have Z's, we need to like introduce gamma and beta into the computation. We need to compute the summation and the average value, subtracting, right? All these computations, Z bars, and a bunch of computations. So this batch norm means that we need to like when we in the backward stage, we actually need to do a lot of extra computation for the gradients, for computing gradients during the backward stage. And fortunately, we have models, we have frameworks implemented that automatically for us. Okay, so the question about why does batch norm work? Okay, remember, the purpose is that it trains the model much faster without compared to the case without batch norm. So the reason that people have come into conclusion is that it's just like the way we normalize input, we can avoid narrow contours of the parameter space. The second reason is that we avoid internal covariance shifts, which means the later layers are less dependent on earlier ones. Okay, so and also it makes the optimization landscape much smoother. So if we look at the paper that people have done research on, like comparing standard models without with the standard models without batch norm with the blue ones with standard plus batch norm, we'll see that the loss landscape will be much smoother, right? And the gradients predictiveness is also much smoother, which means the gradients are much more predictable. So there's not a lot of random walk in a parameter space if we apply batch norm. Okay. And another technical detail about batch norm is that there are not as many data at testing sign. So if we are testing the, so after the training is done, how do we measure the, how do we apply the batch norm during the testing time? Is that we estimate the average mu's and the sigmas from the training data. Yeah, in a mini batch, right? From the mini batch, we directly estimate the mu and the sigmas, and we accumulate them, and we compute the mean values for the mu's and for the sigmas. And given a test example, then we will not use the mu's and sigmas from the test example, but from the average mu's and the sigmas from the training examples. So in the testing stage, the z bar will be computed like this, and z tilde like this. Okay. So more effects about batch norm. Actually, it can dramatically accelerate the training of deep network, like a deep neural network, and the testing accuracy. Like first, let's look at the converge speed. Okay, so without batch norm, it increases somewhat with a slow slope. Like before we reach the highest points, there's still some way to go. Like before 20,000 iterations, training steps. Yeah, but with batch norm, it's just with a few couple iterations, it just reached the best testing accuracy. Okay, so this is results from the original paper. Okay, and you may see that from this plot is that the batch norm also have better testing accuracy, which is basically the higher level, which is basically higher than the no batch norm condition, which says that it also serves kind of a regularization method, right? Because the testing accuracy is better. Okay, it's also regularized the model and can kind of helps reduce the need for dropouts. Like it reduces the risk of overfitting. Okay. So the basic idea is that, well, if we train a model in conjunction with other examples within the same mini batch, then we basically rely less on certain particular examples, but we rather look at the whole data points in the training in the mini batch as a whole set. And in batch norm is also like implemented quite conveniently in PyTorch. We can directly call this batch norms function, batch norm 2D functions quite easily. Okay, so other optimization like weight normalization, layer normalization, these are more fancier ways, and people are still doing experiments over these kind of different normalizations in order to make the training more stable and accurate, I mean efficient. Okay, so actually these hyperparameter search should appear in an earlier place. I think I misplaced the slide here. So it's a way to like how to systematically find hyperparameters. Like if we don't know how to determine the number of layers or mini batch sizes, like we can plot some scatter plots and randomly, and then we train models for those different combinations, and then we will zoom in to find the best positions to decide the model's architecture. Okay, and for learning rates, it's really not a linear space search. We like basically search in the exponential space, right? For linear rate, for the learning rate, we can search over these combinations. But as most of the models published by people, they usually come up with defaults. They are published with default code and default learning rates. So unless you are doing something totally from scratch, then it's not necessary to do a very complete hyperparameter search in practice. All right, so in the last few slides here, I have listed the techniques that are included in this slide, in this course, I mean in this chapter. And these parameters and hyperparameters is something that you can, that we actually nowadays rely a lot in order to make a model trainable and easily extended to with performance, with stable performance and reliable performance on testing sets. Okay, so that's pretty much for the deep neural network chapter. And I'd like to take any questions if you have one. Okay, latest homework about backpropagation, right? Yeah. Do you want to type or do you want to go ahead and speak?
You did type his question.
Yeah, so
Oh, go ahead.
So one of the questions was to display our accuracy, I think. And I think we're supposed to compare predictions with Y-train. Are we supposed to do that?
I think it's Y test.
Oh, with Y-test.
Yeah.
Okay. Well, thanks.
Yeah.
I had a question about that same question. So I got the correct accuracy, but I guess there's like a discrepancy between the cost and the expected cost.
Mm-hmm.
So yeah, I don't know if I did something wrong in the previous tax, or you know what the issue is, but yeah.
Mm-hmm. So I think Jacob has a suggestion that replace prediction from assignment 3 with the predictions initialized. So Isaac, you said you have questions about your problems with the costs.
Yeah, like it says like, so you know it prints the cost after each, like every 1,000 iterations. For example, like after cost iteration 1,000, it prints out 0.27, and then yeah, but then the expected output says the cost after iteration 1,000 is 0.24.
So that's a slight miss, right?
Right.
Slight mismatch. I think that is okay.
Yeah, but then but the accuracy that I print out is like, it's the same one that it's expected in the output.
Mm-hmm.
Yeah.
So the cost can be different, probably due to the different software or different platforms as the code that's run on my machine. I don't know. As long as the testing accuracy is the same one, almost the same one, I think the cost is okay. It's okay. The cost be different values.
Okay. Thank you very much.
Yeah. Okay, it's okay that the accuracy is off slightly. Yeah. Okay. Could be the difference between caused by different NumPy versions, Windows versus Mac. All right, I'm gonna stop the recording right now.